Chekukna. Okay, my name is Chekukna at Rutgers University, resource associate, and
My name is Cristiano Firillo. I'm a research associate with the Department of Civil Engineering at RIME.
Hi, my name is Pen Lo. I'm from Rutgers also, right?
okay. Today, Hani Nassif, the professor and director of our group, supposedly present this presentation, but he has other important meeting today. So, and he was planning to introduce ourselves and also the project, but because of some technical issue, he's not able to attend. He can present. He's here, but he cannot present. So I'm initiating this presentation. So the title of our project is for the CO2 Smart is monitoring and control of overweight trucks for smart mobility and safety of freight operations. So just the background of this project is that the truck weight is important for the safety of the people and then the cars, and we have been collecting and processing the WIM data in New Jersey over the last 10-20 years, and what we noticed is that the average weight of the truck is almost the same as you see in the figure. The mean value is almost not increasing over the last couple of years, but the maximum value or the 90 percentile of the weight increasing over 1 or 1.5% every year. So this is a lot. So we have to know how these overweight trucks are impacting on our infrastructure. Another thing is that the overweight trucks are normally regulated by the weighing station. In New Jersey, there are a couple of weighing stations, and the troopers are trying to enforce them, having them weigh at the weighing station. However, they haven't captured about less than 1% of overweight, but in reality, when we processed all the WIM data, we found that about more than 6% of the trucks are overweighted. So there is a lot of big gap between the actual overweight and what is being cited at the weighing station. One last thing is that because of these overweights, what happened to our infrastructure is that the service life of this infrastructure, bridges, pavements are reduced. On the right bottom one, you just see that the infrastructure lifetime service life is supposedly 75 years, but because of this overweight, it reduced to like 25% or up to like 45% or something. So we have to make sure that how to control these overweight trucks in order to maintain our infrastructure safe and in a good shape. For this study, we had a previous work in New Jersey called the impact of freight effect on infrastructure in New Jersey. And based on that research, we have expanded to New York City, and we are going to share those results in this presentation. First, Graziano will present for the one part of the research.
Yes, related to the impact of freight, generally are two types of components that are analyzed. So one is related to the roadways or pavements, as in structural terms, and bridges, like the structural integrity of the bridge itself. So for what is concerned the two systems, there are different approaches because there are two physically that different. For pavement, generally there are two approaches that can be used. One is I think there is some echo. Can you hear me well? Related to this, the methodology is developed in the 60s called the EASL, or equivalent single axle load. That is an empirical approach where the Federal Highway Administration created some methods where they run with trucks over certain specific pavements, and they measure the effect of different loads on the pavement. Based on that, they created the regression, as you can see in that exponential curve, in order to quantify the effect based on the damage onto the pavement. This was a very simplistic approach, but was because the physics of the pavement is very complex to model, that was the only way that we can provide a methodology for engineers in order to quantify load effect on pavements. But recently, we developed mechanistic models related to finite elements and trying to model the entire characteristic of the pavements and environmental factors that can affect the service life. Basically modeling like the asphalt, the concrete characteristics, the soil, and trying to measuring the effect of ruttings or deformation or unevenness over the surface in order to come up with a real, more quantitative and more robust indicators of the performance of the pavement. In our case, we developed for the New Jersey project a method that is based on the called MEPDG, so Mechanistic Empirical Pavement Design Approach, that use this information, as you can see in the lower chart, with the traffic characteristics, material properties, and climate. And then with this information, we will simulate, using the load, a response of the package, the pavement package. And based on this performance, we measure the deflection, and this is used to quantify good or bad performance related to the service life. And then when we have a model related to a single segment, we can try to extrapolate this effect all over the networks in the state of nationwide related to roads and bridges. So in this case, we have a scenario where basically we analyze a specific segment of pavements related to certain paths. So for each of these links, we know the characteristic of the pavement, and then we quantify the FED, and based on the cost that we have to repair the pavement and the cost that is related to the effect of the trucks, we can quantify how much it would cost to repair the pavement based on the characteristic of the actual trucks that we see on the highway. So this we can do when we know the effect, so when we know where the trucks are traveling. So for instance, we have in New Jersey a database of trucks that basically are known to be overweight, and they require a permit because by law you are required to ask a permit if you know that you're running overweight. Based on these characteristics, they store this information in the database. Using these characteristics in the database, we can quantify how many of these trucks are traveling over in the network and what is the effect, on a year basis, on a monthly basis. So we see that, and we estimated a range based on the effect of these trucks that on my cost at the range between 2 cents, almost 3 cents to 5 cents for interstate, and for state roads we have like almost 10 cents to 50 cents. And on the average we have 4 cents and 25 cents. In order to perform this analysis, we had to assume certain parameters because the diversity of the payment databases all over the state and the cost information are different. So city by city, we can have different cost information. Region by region, we can have different cost information. So based on this, we collected what is available out there in order to perform evaluation of the payment cost damage. One, what we developed in New Jersey, we tried to tie this information to New York City. Differently from New Jersey, in New York City there is no database of trucks where we can infer the patterns of these trucks. We don't know what is the weight related to this overweight unless we measure directly. So there is not like the DOT doesn't track this information yet. So because of that, it was more challenging to perform the same type of analysis in New York City. So we try to assume whatever would be similar related to the two geographic regions. For example, New York City and New Jersey, they share same environmental climatic conditions. So those things were fairly good in terms of related to what we had in New Jersey. For what concerned the trucks, we have to measure trucks in the city, and they have like 3 websites where we could collect data. That is not definitely enough. If you compare that in New Jersey, we have almost 90 WIM sites where we can collect truck traffic data. And the pavement information in terms of construction are similar between New Jersey and New York City. So based on this information, we only have a site-specific traffic information in New York City, while the rest of the information on pavement are basically taken from the New Jersey study at the moment. But there is like in, a follow-up study that we try to collect more site-specific information in the city in order to improve the quality of the estimates. So we can say that approximately we have like 34% higher impact in New York City due to the traffic load than New Jersey. For what is concerned now instead of for bridges, so the effect is completely different. So the way we model bridges is different than pavement. So we have a different physical model, different mechanism of failure. So we have overstress or fatigue mainly, and tied to the effect of the deterioration that generally tend to accelerate the risk or the probability of failure related to either overstress or fatigue. So we have different type of bridges. The most common bridges in the northeast of the United States are the steel girders and concrete bridges. So mainly steel multi-girders. I mean, there are also different typologies for steel bridges. But basically, what we did, we clusterized this information according to their characteristics. And based on the statistics of the bridges, we analyzed a sample for each bridge type in order to come up with the deterioration profile for each component, like superstructure that is divided by deck and overall superstructure, and substructure which contains like piers, abutments, and foundation. And then we develop a methodology that tends to filter the data to perform, based on the statistics we have on the inventory of these bridges, deterioration profiles. So that over time tend to reduce the condition of bridges, and then we can extrapolate the behavior on the long term. So as you can see on the left, we can have like WIM station in New Jersey that were different than New York City, and on the right you can see the flow chart related to the procedure to perform the analysis for the deterioration of the superstructure and substructure. So these are like the results related to the effect of the track weight and the deterioration of decks. So as you can see, so as the equivalent load increases, we have like an effect of the counting effect of the axis that is increased as well. So this is important for the evaluation of the pavement. And these are just examples of the deterioration profile for different type of highways, bridges. So like interstate, where they have high traffic high traffic frequency, and then US numbers, and like local road and state. So on the average, you have like these dot spots, these red spots that indicate the life. So for the interstate, we have an average of almost 40 years for the deck. That is fairly, correct, because generally federal highway require changing of a deck every 40, 45, 50 years, depending on the condition. And this tends to increase as we move to less traffic roads. Again, other different, similar type of curves of the deterioration profile, but just for the superstructure and the girders of steel and pre-stressed concrete bridges. Then we have specifically in New York the location of the WIM site, where we had information about tracks. So we had three, as I said before, points of collection. So one is the Alexander Hamilton Bridge in Van Damme and in Rockaway, so near the airport. As you can see from these statistics, we have like a very high average on the Alexander Hamilton Bridge with almost with more than 10,000 daily truck traffic per day, and the percentage of overweight that is close to 10%. If we go to like less traffic roads like in Van Damme and Rockaway, we have a lower percentage, a lower frequency of trucks, but we can see that we have a higher percentage of overweight. So generally, because truckers, I mean, they know where the WIM location are on the interstate, and they try to avoid bypassing this, going to secondary roads like Van Dam and Rockway. So again, example of the data that we collected for bridges that we analyzed in order to characterize the same type of deterioration profile in the city at each location, in order to tie the effect of the wave motions or the track to the deterioration of the bridges to see if there is any correlation. So you can see we have like an average value that we obtain from these bridges that were shown on the map, and we can have like an average life, expected life, to reach a value of 4, where is a condition that the Federal Highway requires to provide an intervention on the deck, or basically to replace the deck when we reach that value. So the minimum, the value that we can expect to see on the life is 4. Although it can go below, but generally at 4, the Federal Highway requires you to rebuild the deck or any other element like superstructure and substructure. This is again for Van Dam, same type of approach. We have more or less similar deterioration profile, and this is Rockway, and the about 35 years of life for reaching 4 on the average at Rockway. And then, I mean, there is like bridge life cycle that Fong will describe in detail.
Right. So previously we were talking about, discussing the service life and the of the bridge and the pavement. So now we're quantify the service life into the cost. So this is a typical cash flow diagram for the bridge life cycle cost or the pavement life cycle cost. We have the initial agent cost, and then annually we have the maintenance, and after the condition was downgraded to a certain point, we need to upgrade it or rehabilitate those bridges or pavement at certain time. And then we break all those costs into a uniform equivalent uniform annual cost to get the annual cost attributed by the overweight. So here we constructed 2 scenarios. The case 1 is the all truck with represented the current traffic with all the overweight trucks, and the case 2 is the base case, which is only consists of legal truck, which means the service life only under the legal trucks. But the case 2 is the imaginary cost, imaginary scenarios. Luckily, in New Jersey, we have like 93 WIM sites all over the New Jersey, and some of the bridge near the WIM site, they barely see the overweight trucks. So that could be a baseline or the benchmark for the case 2. And Gazena has talked about how we get the service life for the case 1. So here's also some assumptions. The NS period, we use 75 years, and discount rate is 3%. We don't consider the annual maintenance cost at this point, but we assume they are the same for both scenarios. And the deck cost, the replacement cost is $600 per square foot. This is the data given by the New York City DOT, and we assume the traffic increase is 1.5%. Of course, at a certain level it won't increase all the way, but we have a threshold of the maximum truck traffic, which was specified by the AASHTO. So we assume when the truck traffic increase at that point, it will stop increasing. So this is a chart summary all the important parameter of the life cycle cost to calculate the damage cost. So we did it for the deck, we did it for the superstructure, and we did for the pavement. So this is 3 road site, which this cost represent the approximate average damage cost at those 3 sites. So the case 1, we have the service life with the overweight, which is 41 years, 40 years, and 35 years based on the processing of the MBI data. So case 2 is a little bit tricky here. We don't have too much data for the New York City, and we only have 3 sites. So we borrow some previous established semi-empirical, mechanical model from New Jersey. So which means based on the truck traffic observed from the WIM data in New York, we can kind of get the service life reduction using that model. If we go back to that correlation in New Jersey, we have found, so this is a correlation between the WIM data and the deck deterioration on the, if you can see on the left figure, the vertical is lifetime axis count that the bridge deck can sustain, and the horizontal is equivalent vehicle load, equivalent well load, which is an important mechanical parameter indicator. In this case, this is look like similar to the fatigue phenomenon. So based on this, I would call it semi-empirical and semi-mechanical model, we kind of know if you given the truck traffic, how much life you will have. So we're using this chart borrowed from New Jersey, and we can get the service life reduction, which is on the fourth column. And using this service life reduction in case 1, which is we got the real, service life, we can back calculate the case 2. I know this is, but this is the best we can do in the case of New York City. We don't have much WIM data. So for each case, we'll calculate the UAC, which is equivalent uniform annual cost for case 1 and case 2, and we subtract that and divide by the total tonnage, annual tonnage crossing that bridge. We get the cost in terms of dollar per ton and per deck square foot. So this is so if you look at this chart, summarizing, so it's the bottom box plot is the New Jersey cost. So this is for interstate. This is the second box plot is for the U.S. number, and the third is the state. We can see that based on all the assumption we have and all the data we got, New York is way higher than the New Jersey, in terms of damage cost. And in the middle, we have a simple, quick, example of how we implement those damage costs. So if we have we got the unit cost, and we know what's the tonnage of this overweight trucks, and if this truck is crossing, for example, a 60-foot long and 120-foot span, we have this is total 5,000 total square foot of the deck, and we calculate a single trip cost. So yeah, this is pretty much cover the the current stage of the study. So we have some a summary and the conclusion. After this, Chico can talk about the implementation of the high accuracy WIM system. But I'm going to go through this. Monitoring the impact of overweight trucks on infrastructure in New York is challenging because lack of the adequate data. We don't have much WIM site. We only have 3 WIM sites to cover all the areas. The current condition and construction cost of the pavement project were not readily available, and the assumption were made. We need assumption to go ahead with the analysis to get the kind of quantitative result, like make sure the damage cost is in the right magnitude. The current approach for estimating unit pavement damage costs in New York City and New Jersey assume the pavement structure and deterioration characteristics are the same. But for the next step, we're going to get more pavement data. We're going to get more pavement deterioration data to keep updating our model to make the result more accurate. The third one is the fourth conclusion is current analysis of New York City. Again, is limited to only 3 sites. So right now we're working with New York City DOT to install more WIM sites, to expand the data set to have a more comprehensive result. And with more WIM data, of course, we will have a better estimation of the overall damage condition. Yep.
Okay. All right. So after our work here, we are trying to implement the advanced WIM motion, so-called, is like a highly accurate WIM system in New Jersey or New York City. So in order to supplement the data that needed for the additional analysis for the pavement and the bridges. So just to I just want to give another small, presentation explaining about the system sensors that are on the market and how we are going to do in the near future. So first is about the WIM sensor technologies. There are a couple of different type of WIM sensors. The most popular sensor is PVDF sensor, which is piezoelectric sensor that the mechanical pressure is converted into the electric charges, and that is proportion, and that's how you can measure the weight. This is very cheap sensor and is very easy to handle. However, it's cheap means low accuracy, also short service life. But this has been using in many states, and especially in New Jersey, over these 93 sites. The majority of them are, I think, most of them are using these PVDF sensors. And New York City, those two sites, Vendome and Rockaway, is using these PVDF sensors, and the other, Alexander Hamilton, is using, I believe, low cell, no, low cell quartz sensors. And another similar type, which is piezo type quartz sensor, is at the bottom. This is new technologies have been developed in like 5-10 years, more or less. And this is also piezo type, but the medium to measure the weight is the quartz, and it is enclosed in a solid enclosure so that it is not affected by any other external factor. So it is quite expensive, but it provides good accuracy in terms of weight and or other information. And previously, the low cell has been used widely for the high accuracy, but this one is also very expensive and is difficult to maintain. And there was one accident in I forgot where it was before, but the low cell, this one was popped up while the traffic is going over it, and there was a big accident. And the state agencies are trying not to use this low cell anymore on their highway system. And the last one is the bending plate. It has the steel plate with strain gauge underneath to measure, to transmit the strain into the weight. This is also relatively high cost. It's not as expensive as low cell, but as expensive as the quartz sensor, but it's providing less accuracy than low cell and the quartz sensor. So among those sensors, this low cell and bending plate and PVDF sensor, the first one here, has been used widely, and recently for the accurate system, people are trying to use this quartz sensor for easy maintenance and relatively low cost compared to this low cell or bending plate. And in terms of system, the European countries has many vendors who develop this new system. And Czech Republic has system, and the UK also has system, and Czech has two systems actually, CrossWIM and Kami WIM, and they are providing good accuracy, like gross vehicle weight up like 5% using core sensor, and they are flexible to implement other type of system together, for research purpose, and have been using for some enforcement example on each country. And IRD is the Canada, and is is like almost also in US. They also provide like this type of the enforcement enabled system, but they don't provide the accuracy how they can offer. Like if you look at other WIM system, they offer like 5%, 3% gross vehicle accuracy, but they don't have it as of now. On the right side, you can see how the system looks like. More or less, the systems are like slot type, 19-inch rack, and they can expand the slots depending on the number of lanes or application. Okay, and within this system, there have been implemented some enforcement in different countries. Not in U.S. There is one in Indiana DOT. They have one site to implement this type of the WIM system. I don't have the detailed information, so I cannot present here. But one example can show is South Korea. They have 3 WIM sites having this high accurate WIM system for enforcement. They have like 2 lanes, 3 and 4 lanes depending on the location, and they have implemented the quartz sensor with a piezo loop, no, sorry, piezoelectric sensor to track the position of the truck to improve accuracy, as well as they have also loop sensor to identify each vehicle, and also thermal sensor to check the temperature differential between top and bottom of the pavement. So based on their study, the initial results of the calibration truck, the error was up to like 10%, but they were able to update the data to minimize the error by implementing the location of the wheel within the lane, or check the temperature differential between top and bottom. They were able to reduce the error and can obtain up to 3% error in a gross vehicle weight. And they have tried this one in Korea, but they are not actually using for automated ticketing. Rather, they just show the instant notification to the truck driver on a VMS, variable message sign, so that the truck driver knows that someone is watching on them, and they feel that they have to follow the regulation on weights. And similar implementation is made in Netherlands. They also have the quartz sensor, and they also have this piezoelectric sensor to check the position of the wheel within the lane, and they have the loop also to identify each vehicle. And they have implemented this, and they found that at 2 to 4% of gross vehicle accuracy. And similar to Korea, they are not using this for the automatic ticketing, but they are collecting this called vid-WIM. It's that video WIM, because they collect the footprint of the truck itself when it is violated, and they compile those information and collect the trucking company, and they send the like a warning or notification to them in order for the trucking company be aware of the situation, and so that the truck driver do not overload the truck. And one result I want to share with is the result from Korea. After they have implemented this technology on 3 sites, there. By the way, this is ton is in kiloton. Is a bit different from US ton, but similar. So it's over 40 ton means over 80 kgs, which is the federal highway limit. And between 40 to 44 before implementation, this 44 is assumed as a legal truck. But if over 44 ton, over even 46 ton, which is almost 95 kgs, it's very heavy load. So they have tested over 16 weeks from first week up to 16 week, and the number of trucks will remain the same, about 70,000 trucks per each period. But the 40 to 44 ton, which is about 80 to 85 kgs of gross vehicle weight, is keep increasing in terms of numbers. But the higher overweight trucks, over 44 or even 46, is decreased, tremendously. Although this is not actual enforcement, the truck driver knows that this is happening, and they talk, the word spreads, and they are trying to either avoid these sites, or they reduce the weight to comply the weight limit. So for this implementation, we are trying to do some kind of implementation in New Jersey. And we are currently collaborating with different vendors, including Kessler and this Kessler WIM Detlogger, or the new Constack WIM system for field implementation. The vendor produced the WIM system that offers less than 5% error in gross vehicle weight, coupled with this quartz sensor. And we are trying to do some implementation in New Jersey or New York with the DOT or New York City DOT. And this is about potential configuration of the advanced WIM system. And we will use the quartz sensor, and left one shows the full lane, which means we have 4 sensors for per lane, and each axle will measure twice, and also each wheel will measure twice. just as if you average them, you will get a better result. On the right side, if we are limited of the budget, we have to use half a lane, which means we measure only once for each fill, but twice for each axle. So the accuracy on the left is better. So we are trying to do the implementation on the at the configuration on the left side. And where we're going to implement this one is that we have the current website at I-27 in Bedminster Township in New Jersey. We have, and this figure is the actual instrumentation that we made on last spring, and we have been collecting the data and see how the truck traffic is and how heavy they are, and this is 5 lanes. We instrument only two right lanes where the trucks mostly travel on, and we are trying to expand this WIM site with the core sensor of 1 or 2 lanes to compare the accuracy between this piezo, the PVDF type sensor and core sensor, and also as well as to check the feasibility of this A-WIM system for future enforcement. So that's it for the presentation for today, and so I'd like to thank to the City Smart Center and also the Turnpike Authority for providing the cost sharing budget, and also New York City DOT and New Jersey Department of Transportation for providing their database for this project. Alisa?
Okay, so if anyone has any questions from the attendees, you can send them in the chat and the presenters can respond to them. All right, if not, then that's it for today. Thank you to everyone from Rutgers for presenting.
Thank you.
Thank you.
Thanks.